My internet is slow. All right, we are now finally recording. So if I can get everyone to go to the Google Jamboard, I wanted to start here with a bit of just like a conceptual question. It says, under what conditions would a dipole be at rest in a uniform electric field? And so I want you all to answer this question. And for those of you who haven't used Jamboard before, you can go over to the left here. There's the sticky note button. You can just like type out whatever your answer is, and you can make it any color you want. And I don't know, when you type your thing, press save, and then everyone can see what your answer is, what your sticky note is, but no one knows who you are. So don't be afraid of guessing. I just want to get an idea of, what do you think? What types of things would make a dipole be at rest, be still in a uniform electric field? And so it's really hard for me to know how much time you will need for these types of questions. So what I'll do, and I can't see you like clicking or writing or anything, I'm going to put a message in the chat that says ready to continue. Okay, there, it just sent. And so once you've put an answer or a couple things you can think of, or maybe you're stuck and you're not really sure, but once you're ready to kind of move on and have a discussion about it and then go on to the next thing, can you just like react with a thumbs up or something like that to my message in the chat? And that way I'll know that you're ready to move on. So I'm not cutting anyone off. Okay, I see some good things up here. So we've got if the dipole is aligned or the poles are in line with the electric field, yeah, for sure. So if the, I think I can draw on this. Well, I'm able to, I don't know how well it'll go. So yeah, if you have your electric field lines that are something like this, and you dipole, so I don't know, maybe there's a negative charge connected to a positive charge, or maybe it's a continuous charge distribution, I don't know. But in any case, yeah, if it's like parallel or in line with the electric fields, then it will keep from rotating. An equal amount of torque on both sides. Okay, that's an interesting one, because if we had a dipole like this yellow one, for example, so if this was a dipole, and we'll say our electric field lines are pointing up, just as an example. Here, we would have a torque applied to the positive side, drawing it. Oh, oops, I put that in the wrong direction though. Sorry, the positive side should be attracted towards, or like the force should be in the same direction as the electric field lines. So the force, and also like the force on this positive side would be in the direction of the field lines. The force on this negative side would be kind of going opposite the field lines, or anti-parallel. And so here, if these, the plus and minus charges or the same size of charge, then they would have an equal amount of torque on both sides. But since the forces are in opposite directions, you would have a torque, on this positive causing it to rotate this way, on the negative causing it to rotate that way, and I really hope there isn't too much of a lag, or else it'd be really awkward. You hear me say like this way and that way, and you don't see anything. I don't know. I hope you all understand though. In any case, in this type of situation with a positive charge on one side and a negative charge on the other side, like the forces are in opposite directions, but that causes it to rotate in, either counterclockwise or clockwise. That's one to be careful about. The comments about the pole being aligned with the electric field, that's great if my question only said under what conditions would the dipole not rotate. So now what I want you to add, so don't delete the sticky notes you already have, because those are super important for it to not rotate. But what if the dipole also had to not accelerate? Can you think of any conditions or any special cases in which that could happen? You can think of specific examples, like what if you have a dipole with between 2 point charges, or between 2 parallel plates. Or you could think of more general examples, thinking about whether it has an initial speed or not. So just take a minute or two and think of in what case would it also not have some acceleration. And I'll give you another ready to continue message in the chat. I see. Maybe if there were 2 electric fields, can you add another sticky note to that to give an example of what type of thing you mean? And don't worry if you want to just guess too, whether it's right or wrong, you can still learn something from it. I'm seeing some really great answers here, and some things that I didn't really think of specifically. So a parallel plate capacitor, but not oppositely charged. So, I'm drawing again. Just gonna move the sticky note down here. So yeah, that's a really good example. If you have two positive plates, maybe. Oh, except it looks like I'm drawing negative signs. Positive, also positive. And then you have a dipole in the middle, however it's oriented. The negative side would be attracted to both positive plates, but the positive end would be like repelled from both positive plates. So yeah, that could definitely cause the dipole to stay still. If there is a similar point charge, plus or minus, close to the ends, an additional repel. Okay. It could be an additional attractive or repelling force applied. Yeah, that's another really good point. So we'll take my green dipole on the right here for an example. Yeah, so what we're saying is if there's, say, a negative point charge beside the positive end of the dipole and a positive point charge beside the negative end of the dipole, either end of the dipole will be attracted like away from the other, and overall those forces would cancel out, you know, assuming all of the charges are the same magnitude and that type of thing, and the forces would cancel out too. Nice. I really like that one. And so we're saying no force applied to the dipole, yes, because if there's no net force, no force overall, you could have two different forces as long as they cancel out. But then yes, if there's no total, like no force overall, then we won't have an acceleration. Okay, nice. I think that was all I wanted to ask about that one. And so now what we'll do is after having that bit of a brainstorm, let's go over here to the Google drawing page that I sent to the chat. And if anyone has a hard time accessing it or editing it or anything, please do let me know, and I'll send it again in the chat. So here, there's kind of a lot going on just because I wanted to have it set up ahead of time, but I'll explain what the idea is with this. So there's all of these pink and blue lines. They're representing charged plates, and we're going like there's a negative charge plate and a positive charge plate. I just said off to the side on the right here, said we're just going to say that the pink is positively charged and the blue is negatively charged, just as a convention to use so that I didn't have to write plus and minus all over the place. On the left, we have these weird little shape things. Although I'm going to change the formatting a little bit so it's easier for you. Let's make them into a group. So this thing that's in the box here that I'm about to group, this is going to be a dipole. And I'll give you lots of them. So these are just some example dipoles. They have a pink positive charge and a negative charge, that's the blue one. And the negative charge is twice the magnitude of the pink, which is just, I don't know, I made the blue circle bigger to kind of indicate that. And so, okay, in addition to defining a color scheme, just to kind of visualize the positive and negative charges, I've also defined a coordinate system for you. It's not super creative. We have X pointing to the right and Y pointing up. But now we can all be consistent with it. The last thing I want to draw your attention to before I let you go play with this is this text box over to the side here. I've given you a list of 5 different things I want you to try to make your dipoles do, but they're not all possible. So, for example, the third dipole behavior, I guess, is kind of the one, it's the one that we were talking about earlier on the Jamboard, where you're talking about what would it take for a dipole to remain stationary. Given these parallel plate capacitors with a positive charge on one and a negative charge on the other, is it possible for the dipole we've described, or I don't know, these little shapes of dipoles that I've given you, is it possible for it to be stationary between your parallel plates? Or, for example, is it possible that you can put your dipole in the capacitor in a way that when you let it go, it'll rotate clockwise, or counterclockwise is what I said for this first one. And two of them won't happen. Two of them are impossible without some, I don't know, some exterior force or something like that. So this might be a little chaotic, but what I want everyone to do is, can everyone click on one of the parallel plate capacitors just to claim that as yours? I want everyone to, all right, I see someone's clicked on a couple more. Okay, great, we all have one. No one needs to fight over them. So what I want you to do is take some dipoles, and you can drag them into the middle. Yeah, exactly. You can position them where you want. You can put them closer to one side than to another. I realize I haven't given you a lot of space, so if you want to shrink your dipole, that's okay too. You can also, however, rotate it and put it at different angles if you feel you need to do that. So, oh, I'm sorry, I don't know what I did. I think I might have just deleted a bunch of them. Oh, and now they're back. I'm gonna stop clicking things, and I'll give you some time to see what you can make your dipoles do. If you have any questions, feel free to unmute yourself or put them in the chat. In the meantime, I will mute myself and I'll send you a ready to continue message so I can see when we're ready to go on. Oh, I guess one more thing I wanted to say is, so you should end up having 3 dipoles in total, because 2 of the cases that I gave you can't happen. And so can you have all 3 in your capacitor at once? So, you know, if you choose to have cases 1, 2, and 4, just, you know, have them in that order in your capacitor. That would be fantastic. Just so we can compare after. Okay, I'm actually going to shut up this time. So once you've got your dipoles in, and no rush, I just see you've all got 3 dipoles there now. I gave everyone a list of numbers, just 1 to 5 on the left. So once you have your dipoles where you want them, can you just like click and drag one of the lists just over to your capacitor, and you can delete the numbers. So I've listed like the dipoles, you know, rotating counterclockwise or accelerating in the minus X direction. and just delete the numbers that are impossible. So the numbers that you're left with would indicate what your dipole, what your 3 dipoles are doing, preferably in that order. Okay, so it looks like we're ready to keep going. So I see everyone agrees that number 1 and 4 should be included. So the dipole can rotate clockwise and it can rotate counterclockwise. I agree with that. We've got some number 3, so the dipole will remain stationary, and number 4, the dipole will rotate. Oh, I'm sorry. No, everyone agreed on 4. Number 2 is that the dipole will accelerate in the negative x direction. Okay, so let's take a look. So absolutely, if your dipole, as long as it's not like not aligned with the electric field lines, your dipole will rotate. And so whether it rotates clockwise or counterclockwise, that really just depends on kind of what angle it's at relative to the electric field lines. I guess I didn't include electric field lines because I thought they might get messy. I'll add 1 to my capacitor just to show you, or just to give an example. So this black, ooh, I got 2 of them. This black arrow is just an example of an electric field line. And so if I take my dipole, well, here it's perfectly aligned with the electric field. So it's not going to rotate. So the person with this top middle, capacitor, if your first dipole is supposed to rotate counterclockwise, this guy won't. Which, I mean, maybe you have yours in a different order than from what I'm seeing, but just to point that out. If I take my dipole and it starts with a bit of a rotation, just so that the positive charge is kind of below the negative charge. So in this case, the pink will be attracted to the blue plate, and so it'll end up rotating counterclockwise to make that happen. So if the pink starts below the blue, it'll rotate counterclockwise. So this person's capacitor here, at that angle, it's going to rotate counterclockwise. So this would be Oh, I think I said something backwards. Wait a second, what did I say? Okay, for 1, it should rotate counterclockwise. So let me do my example again. So, okay, if it's angled kind of downwards, or the pink, the positive like end of the dipole is more towards the negative plate, it will rotate this way to align itself. Okay. So so as long as the pink is kind of below the blue, then it should rotate counterclockwise to align itself. So this dipole looks good. It'll rotate counterclockwise. This one, I think this one would rotate clockwise. It looks like it's tilted a little bit because this pink is going to want to come down to the blue. So this one should be angled differently. This one's going to rotate clockwise. And oh, that's number 4. 1 is the middle. Okay, 1 middle, yes. This dipole will also rotate counterclockwise. So number 2, the dipole will accelerate in the negative x direction. This can happen. So if it's going to accelerate in the negative x direction, or towards the left. Oh, there's my cat. We pretty much just need, for the negative charge, since it has the bigger magnitude, we need for the negative charge to be closer to the positive plate. So the way that I've put my dipole in here without rotating it or anything, that would accelerate towards the left, because the negative charge has it's a bigger magnitude to the charge, or it's a stronger charge, so the force on this end will be bigger. We'll go to the left. So here 2 has got the negative charge pointed towards the positive plate. Good. This should be for question 2, and then it would be perfect. And let's see, 2 at the bottom, yes, this will also accelerate towards the negative, like in the negative x direction. Okay, so for question 3, I see a couple people put dipoles, but I don't think they would stay completely stationary. So in this case, for this top capacitor, the dipole here will actually rotate. So the positive pink side will rotate towards the negative plate, and the negative charge on the dipole will rotate towards the positive plate. So it might, whether it accelerates or not, it will rotate, so it won't be completely stationary. And for this example here, I see this example here. This is a really interesting example because the dipole is in line with the electric field, so it won't rotate, but it still could accelerate side to side. I guess if it's already touching the plate here, then it has nowhere else to accelerate to, so the plate would stop it. But in this case, it wouldn't rotate because it's lined up with the electric field lines, but it would accelerate. Last, so I guess for 4, it's not last, we have the dipole will rotate clockwise. That just means you take a dipole and angle it differently from the first one. So if I put my dipole up like this, for example, the pink, or the positive charge, is going to get repelled from the other positive and go towards this negative plate, and the negative charge will swing back around the other way. So this this guy here, this dipole, won't actually rotate, again, because it's in line with the electric field, but if it had a bit of an angle, it would. This one, if this is meant to be for, I think, this is counterclockwise. Yes, this would be clockwise. And this number 4, same idea. He's not going to actually rotate, but if you gave him a little nudge, then this dipole would rotate. And this one is also going to rotate clockwise. Okay, nice. So, and I guess the last case was that the dipole will accelerate in the positive y direction, so that's like upwards. And everyone got that right, is that there's no forces acting in that direction at all. So there's nothing that would cause your dipole to accelerate that way. Okay, so before I move on to try a problem or a question, does anyone have questions about either this activity with the dipoles or before when we were just discussing what would make a dipole stay stationary, remain stationary, I don't know, in a constant electric field? So what I want everyone to do is I'd like for everyone to write something in the chat. If you have a question, write your question. But if you don't have a question, then can you just write like all good, or nothing for me, or so just something to let me know that you're good, you understand, and we can do a problem together. Okay, question in the chat says, if the dipole was slightly outside of the entrance to the plates, would it accelerate inwards? That's a really interesting question, and I think that would depend on where exactly it is relative to the plate. So for example, if I take this dipole and maybe if I rotate it like this dipole would be attracted to the positive plate of the capacitor here. So it would probably just go towards the plate. Maybe as it's accelerating towards the plate, it would get into where the electric field is uniform, and that would cause it to align itself with the electric field. Like, that's possible. It's also possible that it would kind of miss the entrance and just be attracted to the plate itself. But yes, if it was outside of the entrance, it would be like accelerated towards the oppositely charged plate. Unless, I suppose, it started somewhere like this, where the negative side of the dipole was really close to the negatively charged plate, then that might be enough to repel it. Okay. All right, so for that first question about the dipole being slightly outside the entrance, does that answer your question? Can you let me know in the chat? Okay, fantastic. There's another question that says, on the Jamboard with the sticky notes, I thought I heard something not quite right. Okay, it's always possible that I said something not quite right. So a dipole would remain stationary if it was in line with a uniform electric field. Oh, I see. Okay, thank you for bringing that up. Yes, originally, when we were talking about the dipoles moving in an electric field, everyone was pretty much only considering the rotation of a dipole. And so at first, in all of these sticky notes on the top here, we were saying that it wouldn't rotate if it was in line or parallel to the electric field. However, when we got a bit more general and said, well, what about acceleration and not necessarily rotating, but actually like translating or moving, then in that case, the dipole can absolutely move. It can be accelerated without rotating. So it can be accelerated even if it is pointing in the same direction as the electric field lines. And actually, if you had a dipole, so we'll draw some field lines here. If you had a dipole that was fixed, so for whatever reason it wasn't able to rotate, then it actually wouldn't accelerate. Oh, am I drawing this right? Oh, I'm drawing something different. Okay, what I'm drawing is that if it's not aligned with the electric field lines and there was something that was stopping it from rotating, it also wouldn't accelerate because it would be like equally attracted and repelled to both sides, like to the negative sides of the electric field here and the more positive sides down here. But to answer your question in more of a concise way, a dipole in an electric field, if it's aligned with the field lines, yes, absolutely, it can move, it can accelerate. It just won't rotate. Does that clear up that question? Perfect, okay. So I need some direction from you. So what we can do now, we've got about 15 minutes. I guess the first thing I want to know is, do you have any questions about something that we didn't go over tonight that you'd like me to talk about? Either something that came up in your homework or in class or something that might be on the test. If there's anything that you would like to ask, feel free to put it in the chat now. If there isn't anything yet, I have a couple types of questions we can, more like, like calculation type problems that we can do. I have a capacitor question and a point charge question. So if there's something other than what we've done tonight that you'd like me to talk about, can you write that in the chat? If not, can you tell me in the chat, would you rather do a dipole in a capacitor like calculation question, or would you rather do a point charge calculation question? And I will let you know that whichever one of these two problems we don't do tonight, I'll do in my PAL session tomorrow night. And if you can't come, you can always watch the recording afterwards. But for tonight, let me know what you'd rather do. Okay, looks like we're going to do the point charge question. Sounds good. So, yeah, we'll just scroll down here. So what we're going to do is look at a very old and very much simplified model of a hydrogen atom. And so I don't know if anyone here has taken any sort of quantum physics or quantum chemistry classes that look at the behavior of these particles and the hydrogen atom in a lot more depth. But what we're going to do is look at a very simplified model where we just have a proton and an electron orbiting around it. You know, like all the cartoon atoms and things that get used on logos, that's what they look like there. So we'll test that out and see how good of a model is it. But that's how we're going to treat our hydrogen atom. So what I've done here is these two lines are just a couple known quantities about hydrogen. I'll make them a different color so they stand out a little bit. That looks exactly the same, but it's fine. So the atomic radius of hydrogen is about 10 to the minus 10 meters, or 1 angstrom, it's called. So we have a little tiny proton, and at like a circle, approximate circle, of a radius of 10 to the minus 10 meters, we have this little itty bitty electron. There's a teeny tiny dot there. That's the electron. And so this atomic radius, well, it's much bigger than the size of the proton and the electron itself. We can treat that as like the distance between them. And we can definitely treat the electron and proton as point charges. Something else, another tidbit of information, is that the ionization potential of the ionization potential of hydrogen, which like ionization potential, if you haven't seen that terminology, it's just like the potential energy between like of the proton and electron system, and it's 13.6 electron volts, which is equal to 2.18 times 10 to the minus 18 joules. I just gave the answer in joules because the units tend to work nicer that way. So my first question says neglecting any gravitational forces, which is totally fine to do. Like the proton and the electron have such tiny masses that they don't exert much of a gravitational force on each other at all. So we're going to pretend the gravitational forces just don't exist. And we're going to assume that the electron has a perfectly circular orbit, because that also makes the physics a bit nicer. So my question then says, what is the minimum distance between the proton and electron? So, and a minimum distance in like a number value, like an actual quantity is what we're looking for here. So this probably seems a bit ambiguous. I haven't said, use this value for charge, this value for speed, this whatever. But all of the values that we'll need here are like constants or like commonly used values. So first, what I suggest doing is let's kind of set up the equations that describe our model. The model being an electric force, which is holding this electron in a circular orbit. So let's describe this model mathematically, and then we'll see what information do we need to find. Because, for example, something like the charge on the electron, that's something you can look up. You don't have to actually go and calculate that. So we said that the force, this is going to be the force on the proton that we'll talk about, because the I'm sorry, I think I just said proton. I meant to say the force on the electron, this little bitty electron here, because it's the one that's doing the orbiting. So the force on the electron coming from the proton, that's going to be, well, we can calculate that, I guess, using Coulomb's law. So we have that the force is equal to, I usually just use K, but you can also use 1 over 4 pi epsilon naught, but I go with K. Then you have the charge of the electron times, I don't know why I wrote P, times the charge of the proton. And the proton, I'm just doing a subscript of P with a little plus sign because it's a positive proton. And that is divided by the distance between them squared. So this distance can be R. But since the electron is moving in a circle and it's undergoing circular motion, we can kind of like equate this to the centripetal force equation and say, well, this electric force is causing the electron to move in a circle, and that means the force exerted is equal to mv squared over r. I just about panicked here because I thought my r's are going to cancel out, but I realized that I forgot a squared in the denominator for the electric force. So before we go looking for numbers and quantities and things, let's simplify this a little bit. So the charge on an electron and on a proton is actually equal. That's why hydrogen atoms are overall neutral. So we can say that K QE squared, or since it's the only charge we're looking at, let's drop the subscripts and be lazy and we'll just write KQ squared over R. Just I'm going to cancel out with one of the r's on the other side. That's equal to mv squared. And so we're looking for the minimum distance between the proton and the electron. So I'm going to isolate this, or like rearrange this equation for R. So I'll have that R is equal to KQ squared over mv squared. So we've set up our model in an algebraic way by equating these forces. Then we've simplified the equation and we've isolated for the quantity that we're looking for. Okay, and I've made myself some more space, so we're ready to keep going. Now let's see, what values do we need? What values do we have? So this K is a constant. You can look it up. I think it's about 9 times 10 to the 9 newtons per coulomb squared or something like that. I don't remember the units exactly, but it's about 9 times 10 to the 9. This Q, so that's K. Q is the charge on the electron. That's another thing you can look up. It's equal to about 1.602 times 10 to the negative 19 coulombs. I do want to point out that even though I don't remember what the units of this K constant are, they are SI units, so they'll play nice with the coulombs and the meters per second and that type of thing. So it is the right units, I just don't remember what they are. The mass of an electron is another constant, and that's about 9.11 times 10 to the minus 31 kilograms. The last thing we have here is this V squared. And this V is actually going to dictate what the minimum distance between the proton and the electron is. Oh, thank you. K equals 8.99 times 10 to the 9 Newton meters squared per coulomb squared. I was close, or I would have been close if I had kept it. This is why you never erase your work. Newton meters squared per coulomb squared, although that shouldn't be an equal sign because these are just units. Goodness. Okay, thank you for looking that up for me. I appreciate it. All right, So the last thing is this v. And in the question, it didn't tell you that it's moving at a certain speed, and so what is the exact distance between the proton and the electron given this speed. But what it's asking is, what's the minimum distance possible? And that actually depends on the maximum speed possible. And well, the maximum speed that, well, I should say it in a different way. There is a maximum speed that anything in the universe can travel at. I'll give you a minute. In the chat, do you know what that maximum speed is? And you can give the definition if you don't know the number. Do you have any idea what that, like the biggest speed that nothing can go past? Speed of light, yes. Yes, exactly. So the fastest possible speed that this electron could be going is, well, like technically just less than the speed of light. So what we'll do, this is equal to m, what we'll do is we'll plug in the speed of light here. So we'll say the speed of light, the electron has to go slower than that. So whatever distance we get, the distance technically has to be bigger than that. So we're getting like a really like lowest possible estimate. So v is equal to, well, and the speed of light is about, well, it's like 2.997 or something like that. So I'm going to call it 3 times, not 8. 3 times 10 to the 8 meters per second. And so if you take these values and plug them all in, that will, based on the model of an electron orbiting the proton in a perfect circle, based on that model, these will give you the, like, what's the smallest possible distance between the electron and the proton. So there is a bit more to this question. And there's also a capacitor question that I made up. And so I think we'll save those two problems for tomorrow's PAL session as like preparation for the test on Wednesday. So with that, I'll stop sharing my screen and end the recording here.